Welcome to The Explainer. Today, we're talking about a breakthrough that could be one of the biggest, well, ever. We're talking about a discovery that could totally change our entire relationship with energy.
Okay, before we geek out on the physics, let's just start with a dream, right? Let's picture the world this thing could actually create. A world without waste. And look, this isn't science fiction, this isn't some pie-in-the-sky wish list. We're talking about power grids that can send electricity across continents with literally zero loss. Trains that just float silently, with no friction. Quantum computers? Yeah, small enough to pop on your desk. That's the absolutely incredible promise of room temperature superconductivity. So what even is superconductivity? Okay, think about it like this. Electricity in a normal wire, it's like water trying to flow down a super rocky stream. It's bumpy, it's chaotic, it loses energy along the way, and that lost energy, that's heat. But in a superconductor, that rocky stream becomes a perfectly smooth, glass-like river. The electrons just glide along in perfect sync with absolutely zero resistance. No energy wasted. None. That sounds perfect, right? It's basically the holy grail of physics. So you've got to be asking, if we've known about this for more than 100 years, what was the one giant catch? What was the problem that kept this incredible technology locked away in labs for so long? Well, the answer is a big one. It's a story about a century-long quest, this huge scientific marathon, all focused on breaking down one single massive barrier. And that barrier? It was temperature. You see, superconductivity was first spotted way, way back in 1911, but it only worked at temperatures colder than outer space. We're talking just a couple of degrees above absolute zero. Even the high temperature breakthroughs everyone got excited about in the 80s, well, high meant a still ridiculously cold minus 140 degrees Celsius. So for decades, this amazing phenomenon was basically trapped in the ice. And then, 2025, everything changed. The barrier wasn't just pushed a little bit, it was completely smashed to pieces. A material was made that could superconduct at a totally normal, comfortable 15 degrees Celsius, room temperature. For the very first time, this quantum magic was happening right in front of us, in everyday conditions. So the big question is, how? How did they finally do it? Let's meet the team, the Nobel laureates who finally cracked this 100-year-old puzzle. Now, this wasn't some lone genius having a eureka moment in the shower. No way. This was a masterpiece of teamwork. You had Evelyn Reed, the theorist, who basically used supercomputers to figure out what might work. Then you had Kenji Tanaka, the chemist, the guy who would actually build these crazy, exotic materials, literally atom by atom. And finally, Ben Carter, the experimentalist, who built the insane machine they needed to actually test it. So the secret sauce here, the thing they figured out, is all about something called Cooper pairs. Okay, so normally electrons are like grumpy little loners. They repel each other. But in a superconductor, something amazing happens. An electron passes through the material, kind of pulls the structure toward it for a split second, and that creates a tiny positive charge that yanks in another electron. Suddenly, they're a team, a quantum duo, and this Cooper pair just surfs through the material like a single perfect wave. Nothing can stop it. No scattering, no energy loss. For years, the theory pointed to hydrogen. It's the lightest element. It seemed like it had to be the key. The problem? Pure hydrogen is a nightmare to work with. So Reed's big idea, her theoretical breakthrough, was this concept of a hydride cage. Basically use heavier atoms, like yttrium, to build a kind of chemical cage. Then you could trap and squeeze the hydrogen atoms inside, forcing them into the perfect shape for those Cooper pairs to form, but at room temperature. Okay, so they made it. How did they know it worked? Well, the first proof was just undeniable. They ran the test on their new material, and its electrical resistance didn't just get low. It just, poof, vanished. It dropped completely, totally to zero. But the second proof? Oh, that one was even cooler, way more spectacular. The Meissner effect. See, a real superconductor doesn't just let electricity flow perfectly. It actively kicks out any magnetic field that tries to get inside. It becomes a perfect magnetic shield. And that is exactly how you get things to levitate. So, with that temperature problem finally solved, that future we were dreaming about at the start, that door is now blown wide open. We can really see how this science is going to change, well, everything. let's just take the power grid, for example. Right now, today, we waste something like 5 to 10% of all the electricity we make just from it heating up the wires as it travels. It's just gone. A superconducting grid, that waste goes to zero. Imagine all that saved energy, all that saved money.
And it goes way beyond that. This means we can build cheaper, way more powerful magnets for fusion reactors, getting us closer to clean, limitless energy. It means we can have small, affordable MRI machines pretty much everywhere without needing all that crazy expensive liquid helium. And quantum computers? They could finally come out of those giant deep freeze refrigerators and kick off a whole new age of computing.
But you know how it is in science. You break down one wall, and it usually just shows you the next one you have to climb. The journey to get this amazing tech out of the lab and into our hands, well, it's not quite done yet. So here's the thing. The team got the temperature right, which is huge. But there was another piece of the puzzle. They smashed through the temperature wall, but it came with a pretty big catch. 2 million, that's the amount of pressure, in atmospheres they needed to make this thing work. I mean, that's a pressure that is just insane. It's like the pressure you'd find deep inside the Earth's core, and they had to create it by literally squeezing their little sample between the tips of 2 diamonds. And that's why this 2025 Nobel Prize isn't the end of the story. Not at all. It's the starting gun for the next great scientific race, the ultimate quest for the true holy grail, a material that can do all this at everyday temperature and everyday pressure. Reed, Tanaka, and Carter, they've shown us the way. They've opened the door. The big question now is who's going to be the first one to walk right through it?